In lesson 4, we're going to look at complex rational expressions. And what a complex rational expression is when you have two fractions or two rational expressions um, inside of a fraction. So it's a fraction divided by a fraction, or a rational expression divided by a rational expression. So basically, in order to do this, there's a couple ways that you could go about it. Um, so one method for this would be to treat this actually like a division problem, because you would take the top and you divide it by the bottom. That's what this means. This really means 3/4 divided by 5/8. So what you would do is you would multiply by the reciprocal, because remember, whenever we divide, it's really like multiplying by the reciprocal, or when you divide fractions, it's multiplying by the reciprocal of that fraction. So multiply by the reciprocal. Or you can think of this as keep, change, and flip. So we're going to keep the first fraction. So we keep the 3/4, change the sign to multiplication, or change the operation. Then we flip the second fraction. And then again, when we go back to how we multiply fractions, we reduce if we can. So 4 goes into 8 2 times. And then we multiply across the top, so we get 6. Multiply across the bottom, we get 5. So that's one way of doing it. Another method, which is actually, I think, going to be easier when we get to algebraic rational expressions, or expressions with variables in them, is going to be to multiply the top and bottom by whatever the LCD is of all of the smaller fractions. So this method, we're going to multiply the top and bottom of the, I'm going to just put it in quotes here, the big fraction, meaning the entire thing. So the entire top and the entire bottom, every piece in the numerator, every piece in the denominator, we're going to multiply those by, so of the big fraction, by the LCD of the smaller fractions. And when I say smaller fractions, I mean of the fractions within the bigger fraction. So it's a complex fraction because of the format of it. So since there's fractions inside of fractions, it makes it more complex, which is why it's called a complex fraction. So if I look at this problem and apply this second approach to it, so if I had 3/4 over 5/8, you find the LCD of the denominators of the small fractions, which in this case would be 8. And then what I do is I multiply everything by the LCD. So I multiply the top by 8 and I multiply the bottom by 8. And the reason why you're allowed to just multiply an expression by 8 is because since it's a fraction, I'm really multiplying by 8 divided by 8, which really is like multiplying by 1. So I'm not changing anything, because 8 divided by 8 would give me 1. So I'm not changing anything. I'm basically writing an equivalent fraction. So when I multiply this 3/4 by 8, you have to think of this as really 8 over 1. So you look at what cancels here. Well, 4 would go into 8 2 times. So we would have 6 on top, because it would just be 3 times 2 and then 1 times 1. So I'm just going to use the 6. I don't need to worry about putting the 1 underneath. So it's going to be 6 over. And then on the bottom, these 8s are actually just going to cancel and become 1. So I would have just a 5 on the bottom. So that's my answer. So both ways you get the same answer. It's just a different approach. I think this method here is probably going to be your preferred method when you're doing these, because of the fact that it's just quicker, and especially when we get to these problems that have variables in them. So let's use the second method. And what we're going to do is we're going to look at this and we have to first figure out the LCD. And remember, when we're trying to figure out the LCD, we're looking at the denominators of every single small fraction. So all of these denominators have x's and y's, so the smallest common factor between, or the smallest common multiple between these is going to be xy. So let me first just rewrite this so it's a little bit bigger. So I have 1 over x plus 1 over y all over 1 over x minus 1 over y. And what I'm going to do is I'm going to take my LCD and I'm going to multiply everything by it. So every single piece is being multiplied by x times y. And the reason why it has to be every single piece is because, remember, you're thinking of this as I'm multiplying this entire fraction by xy over xy. That's really what I'm doing. So I'm really multiplying everything by 1, so that's why it's okay to multiply an expression by a number. Normally you can't just multiply an expression by a random number. It has to be not changing it, and I'm not changing it here because I'm really multiplying by 1. And then basically what I'm doing is I'm just distributing each of these. So you don't need to show this step. We usually just jump right into here. So now I look at reducing this. So remember, all of these xy's are all over 1. So you basically look at them in comparison to each of these and try to cancel. So here I have x and x, which are going to cancel. And I'm going to have a y left. So I'm going to have a y because y times 1 is y, and then 1 times 1 is 1. I don't need to worry about it. And then here the y's are going to cancel, so I'm going to be left with a plus x. Down below here, the x's are going to cancel, and I'll be left with a y times 1, which is y. Here my y's cancel, so I'm left with a minus x times 1, which is x, and then again 1 on the bottom. So here would be your final answer. And when you guys are doing these, you're going to see that the denominators are going to cancel. That's the whole purpose of this strategy of multiplying by the LCD. It basically eliminates this small set of fractions. So let's look at a couple more examples. So this one here, you first want to figure out the LCD looking at the denominators of the smaller fractions. So in order to do that, you need to factor this x squared minus 9. So first thing I'm going to do is rewrite this. So I have x minus 2 over, I have x squared minus 9, which is going to be a difference of perfect squares for factoring. So 2 sets of parentheses, square root each piece, and it's going to be opposite signs. That entire numerator is over x squared minus 4 over x plus 3. So it's going to be x minus 4 over x plus 3. And then the LCD of this, when you look at the fractions in the, or the denominators of the fraction, the small fractions, we have x plus 3 and x minus 3 would have to be the LCD. So x plus 3, x minus 3, which means I need to multiply each piece by that. So x plus 3, x minus 3. And now you're going to cancel. So you're multiplying the top and the bottom by x plus 3 times x minus 3. And now we look to cancel. So this is going to cancel. So up top, I'm going to have just x minus 2 now. So basically, remember, this is like all over 1 when I'm multiplying. So it's x minus 2, and then on the bottom is 1, but I don't need to worry about that 1 because you're trying to get rid of those denominators. Same with this one. This is really over 1, but we don't really need to worry about the fact that there's a 1 in the denominator. So these are going to cancel. And I'm going to be left with, in the denominator here, x squared minus 4 times x minus 3. And I notice that I have an x minus 2 up top, and I have a difference of perfect squares. So what's going to happen, I'm going to go ahead and I'm going to simplify this. So I'm going to factor x squared minus 4 as x minus 2 and x plus 2 because it's a difference of perfect squares. And the whole reason why I factored is because I recognize that x minus 2 would be a factor. So then my final answer, I'm going to have a 1 on top, x plus 2 times x minus 3. So let's look at just 2 more examples. So in this one here, I'm checking all of the individual fractions and trying to find an LCD. So when I look, remember these ones here are really over 1, so 1 is the denominator. So the smallest number that all of these can multiply into is going to be x squared. I don't have to do x times x squared like all of the other ones. We've been multiplying the factors because x goes into x squared. So x squared is actually going to be the LCD. So I can go ahead and multiply everything by x squared. And when I do that, I'm going to see that this first term here is going to be x squared. These are going to cancel, so I'll have minus 4 on top. On the bottom here, I'm going to have x squared times 1, so I get x squared. For this piece here, it's kind of hard to see, but I had an x with an x squared. So basically, I'm just going to have an x in the numerator. So it's going to be a minus x. And then here, the x squareds cancel, and this was a minus, so it's going to be just minus 6 at the end. So now what I'm going to do is I'm going to go ahead and I'm going to reduce this. So I'm going to factor the top. It's a difference of perfect squares, so it's going to be x plus and minus square root the 4. And then I'm going to factor the bottom as a quadratic factoring. So x, it's adding to a negative and multiplying to a negative. So opposite sign since I'm multiplying to a negative. Bigger number has got to be negative since I'm adding to a negative 1. And then cancel. So reduce anything. So we have x minus 2 over x minus 3 as our answer. So one last one here, just something that looks a little bit different to start. And this is a problem where now we have a whole number and we want to subtract this fraction or this rational expression that has a fraction involved in it. So it's kind of a complex fraction here. So what we're going to do is we're going to simplify this piece first. So let's take care of this and then we'll worry about actually going back and doing the subtraction. So I'm just going to carry that 2 along the way though because I don't want to forget about it. So let's go ahead and simplify this. So we're going to find the LCD. So I'm going to keep it as 3 over x plus 1/3. And I'm looking for the LCD of this piece. So the LCD of this rational expression, well, there's really a 1 in the denominator up top, a 1 in the denominator there. So 3 is actually going to be the LCD. So that means I'm going to multiply everything by 3. So then what I have is 2 minus 9 over 3x, and these 3's cancel, so plus 1. And if you notice, basically all that did was make my new denominator something that didn't have a fraction in it. So if you really wanted to, I could have just used x plus 3 as my common denominator and created this expression of 2 so that it had x plus 1/3 as a denominator. But now the fact that I have this as an easier expression to work with, or whole numbers, it'll be easier to do the next step. So the next step is to find your common denominator. So we need to find common denominator because we are going into adding or subtracting fractions. And in this case, it's subtraction. So that's why you have to have your common denominator. And that common denominator is going to be this 3x plus 1. So the LCD in this case will be 3x plus 1. So this is where, remember, you have to, because this is all over 1, you're going to first recreate the problem where your denominator, your common denominator, is being used. And then you have to ask yourself, well, how did I go from 1 to 3x plus 1? Well, we had to multiply it by 3x plus 1. So that means the top needs to get multiplied by 3x plus 1. Again, because you multiplied the bottom, you have to multiply the top, so essentially you're multiplying by 1. So then you're just going to distribute this through. So you have 6x plus 2. And then over on this side, you don't have to change the denominator, so you don't have to change the numerator either. And now the next step for subtracting fractions, so remember, you keep the denominator, and then you just subtract across the top. So 6x plus 2 minus 9, and then we just simplify. So we have 6x minus 7 over 3x plus 1. And that'll be it. So this one, we use the whole complex fraction technique to help us make the denominator an expression without a fraction. However, you could have gotten to the same answer if you would have just kept the x plus 1/3 in the denominator and used x plus 1/3 as your LCD to create this new fraction and actually subtract the numerators. So either way works, but usually we try to avoid fractions, so that's why using the complex fraction method makes things a little bit easier.